We'll get started,
I'm
and if
ready.
somebody else wanders in, that's fine. If not, we'll continue on anyway. And
Okay.
so same set of notes as we've seen now for 2 weeks. Got those? Someplace in the notes, there ought to be a page that looks like this. Open channel hydraulics. We actually went through that particular page of notes last time.
All I see is you right now.
Oh, okay. You see me then, not the notes?
He's got it now.
I see the notes now.
Oh, okay. And I guess we got a little further Thursday than we did Wednesday. Were you here either Wednesday or Thursday of last
I was here
week?
Wednesday last.
Okay.
Yeah, I was here Wednesday last.
Okay.
We were actually a couple slides ahead of that.
So what we did last Wednesday then, we got started on open channel hydraulics, and we talked about
Right.
channel geometry, we talked about flow
Right.
classifications, we covered uniform flow, and I believe that's where we ended. And so that's going
That's about right.
And so what that's going to do for us tonight is to start with critical flow, and then look at water surface profile computations using the energy equation, and then deal with hydraulic jumps using conservation of momentum. And then that'll take care of the hydraulics portion, and we'll move into hydrology from there.
Okay.
So we've got a full evening, so we'll just do the best we can and go as far as we can. Now this is a very fundamental, basic concept here in open channel hydraulics, and that's critical flow. And we did not cover this last week, I don't think. I think we stopped right before that. Am I right? Do you remember?
Let me look here. They're over there on the.
Well, you're
Yeah,
not
we were just about there. You had just basically just started on Manning, the Chesney Manning, and with uniform flow, and that's really you didn't really even go into the problem yet on that. The example problem you had in there.
Okay.
That's about where we were. So that's right about right.
Okay. Well, we'll just go from
Actually,
here.
it's okay.
And you won't be by yourself.
Oh yeah, we got a partner here now.
Got a partner, so that's great. Well, critical flows can be defined by, I've listed these as just characteristics or conditions that occur at critical flow. You could, if you like, need a definition. Any of these conditions would serve as a formal definition of critical flow. And so critical flows, flow condition when the specific energy is a minimum for a given discharge, or the discharge is a maximum for a given specific energy, or the Freud number is equal to 1. And just a little sideline, the velocity head's equal to half the hydraulic depth. If we're working in terms of momentum instead of energy, the specific momentum is a minimum for a given discharge, or the discharge is a maximum for a given specific momentum. And this is really more along the lines of continuing definitions. Critical depth, the Y sub C is the depth at which critical flow occurs, and then we define subcritical flow, critical flow, and supercritical flow. And subcritical flow, by definition, the depth is greater than critical depth and the velocity is less than critical velocity. So subcritical flow means the water's not flowing very fast. And so any of the natural streams in Texas, you're dealing with subcritical flow. Maybe if you get up into Colorado and the Rocky Mountains where there's very steep, fast-flowing streams, you may have some naturally flowing streams, supercritical flow. And but in man-made structures and the chute of a spillway and a lot of concrete hydraulic structures will deal with supercritical flow. And so subcritical flow, the water is flowing deep and slow. The Freud number is less than 1. Then critical flow, of course, by definition, the depth is critical depth, the velocity is critical velocity, and the Freud number is equal to 1. subcritical or supercritical flow, the flow's flowing fast, barreling down the channel. So the depth is less than the critical depth, the velocity is greater than the critical velocity, and we've got a high Froude number greater than 1. And the Froude number is given there. By definition, the Froude number is the velocity over the square root of d, where d is the hydraulic depth. And from earlier last week, we said the hydraulic depth is area divided by the top width. Now, there are a number of the dimensionless numbers in fluid mechanics, and the Reynolds number we worked with last week in conjunction with pipe flow, and that you'll normally associate the Reynolds number with pressure conduit flow. That's an expression of viscous forces to inertia forces, and the Froude number is an expression of gravity forces to inertia forces, and it's normally associated with problems of open channel hydraulics. And expressing what we've just said graphically, this is a plot of flow depth versus specific energy. And specific energy is the energy with reference to the bottom of the channel. So we're not including the elevation head. We're just including the depth and the velocity head. And so there's a trade-off here between depth and velocity head. And what happens if you change something, and a good example would be maybe changing the bottom slope, the longitudinal slope. And so if we were in a laboratory, we could imagine looking at some sort of a flume or a channel. And in our laboratory here at A&M, we've got such a thing where it's a variable slope, and you can jack up one end and change the slope. And of course, when you make it steeper, the water flows faster, you get a higher velocity and a lesser depth. And in some ranges, a change will result in a bigger change in the velocity head than in the depth. In some other ranges, vice versa. And what will happen is, up here, and this is the subcritical area where we have a depth, a significant depth. Down here is a supercritical area where we've got a shallow depth. And right here, of course, is critical depth. By definition, critical flow is a condition at which specific energy is a minimum. And so for these different depths, specific energy is a minimum right here at the critical depth. And as we change slope or change something, the depth and velocity head will trade off, and we'll get a curve that looks like this. Now, at some point, the 45-degree line, we're asymptotic to that, and we can call these alternate depths. We talk about hydraulic jumps, and we will a little later. These will be pertinent to us then. If we take the concept of the specific energy being a minimum and find the depth at which the specific energy is a minimum, we can go through some manipulations and derive an equation which is used commonly to solve problems. And so on this page of notes, we've written the specific energy, and it's the depth plus the velocity head. And you can write the velocity head v squared over 2g, or recognizing that the velocity is the discharge divided by the area, you can write it q squared over 2g a squared, just plugging q over a in for the velocity. And so if you wanted to find the depth at which this expression's a minimum and to derive the equation that we'll be using, you would set the derivative of this expression equal to 0, and then solve for the, just reduce it down. And so we do that. We're just going through a quick derivation here. Take the derivative with respect to y, and then set that equal to 0, and do some algebraic manipulations. And what just proved to you is that by setting the specific energy, minimizing the specific energy results in the Froude number being equal to 1. And then you can rearrange that a bit and get this equation. And some of the textbooks and references we'll use the equation in that form. The Civil Engineering Reference Manual that you have, as I recall, uses this form, which is common in many references. And so everything from this basic concept, all these steps are just mathematical manipulations, and this is an equation that's useful for solving problems. Q squared over the acceleration of gravity is equal to the area cubed divided by the top width. And the different terms are defined at the bottom there. And so what I'm planning for us to do now is just take this basic equation, and that equation is valid for the condition in which critical flow is occurring. And so in this example, we're saying compute the critical depth and velocity for Q is equal to 400 cubic feet per second. That's the same channel section we worked with last time, the trapezoidal cross section with a 20-foot bottom width and 2-on-1 side slopes. And so we've gone through the geometry of that and have an expression for the top width, an expression for the area. Here's the equation that's derived on the previous transparency from setting Pacific Energy, minimizing Pacific Energy. And so this is the working equation that gets applied in many different problems to solve practical problems. And so we plug in the numbers, the 400 cubic feet per second for the discharge and the acceleration of gravity, the expression for the area, which is a function of the depth, the expression for the top width, which is a function of the depth, and then we solve for y. We have to do that by trial and error. It's a little bit of a messy equation, and we get a depth of 2.13 feet. And so we're not saying that the depth is 2.13 feet. We're just saying if a depth of 2.13 feet occurs, we've got critical flow. Now we've got a depth greater, if the actual real depth is greater than 2.13 feet, we've got subcritical flow. If the depth is less than 2.13 feet, we've got supercritical flow. And the problem statement also asks for the velocity, so we can, recognizing that the velocity is the discharge divided by the area, can plug in for the volumetric flow rate that's given, and then the expression for the area, plug in the 2.13 feet and the critical velocity 7.75 feet per second. Now this whole thing about critical flow is just a natural phenomena, and certain things are related there too. For example, one of the things happens is in the wave celerity. For example, if you want to play a game and throw rocks in a river, and you've got a stream of flowing water, and you can throw a rock in the river and watch the ripples and tell whether you've got sub or supercritical flow. If you throw a rock into flowing water, there'll be ripples that go in all directions from where the rock splashes into the water. Now if you've got supercritical flow, that means the water is really barreling down the channel at a high velocity, and the velocity is going to exceed the wave celerity of the ripples such that there'll be no ripples going upstream. The velocity of the flow will wash the ripples downstream. If you have subcritical flow, the waves, the ripples of the splashing rock that you've tossed into the stream will propagate both upstream and downstream. Now the velocity of the flow will wash them downstream, so they'll be going downstream faster than upstream, but you'll have circles going from the rock in all directions. In a few minutes we'll be talking about water surface profiles, which is a very common type of computation. And when we're doing water surface profiles, we have to start at one location and work our way either upstream or downstream. And in subcritical flow, changes, non-uniformities propagate upstream. And so in water surface profile computations, if you're analyzing rivers in Texas, you're going to always find yourself starting downstream and working your way upstream. And supercritical flow is just the reverse. Nothing propagates upstream. If you dam off any kind of an expansion, contraction, any irregularity, non-uniformity will not propagate upstream. And so in water surface profile computations, you'll be starting upstream and going downstream. Now, this is perhaps one of the most common applications that we relate to the concept of critical flow and super versus subcritical flow, and that's the hydraulic jump. And the hydraulic jump is a very efficient energy dissipator. There's a tremendous amount of turbulence in a hydraulic jump, and the turbulence dissipates the energy. And so in many cases that gets us into trouble because it causes erosion of natural stream banks. In many cases we use it to our advantage to dissipate energy on purpose in an engineered type of an energy dissipator. And so the basic concept is this. This is the basic principle. To have a hydraulic jump, you've got to go from supercritical flow to subcritical flow. I'll not flip back in the notes, but on the diagram you notice when the specific energy is a minimum, we've got sort of a curved surface where there's a very significant change in depth for a relatively small change in energy. The water surface will jump up and down when you get near critical flow. And that's what's happening with a hydraulic jump. It's really jumping up very abruptly. And here we're just looking at some physical situations that might cause a hydraulic jump. Here we've got a gate, and you could picture that as being a highway culvert, water coming out of a culvert, water coming through a sluice gate of a dam, any type of a situation where you've got water ponded and there's some sort of a gate through which the water's flowing, and this constriction is causing supercritical flow. The water's really barreling out of that culvert, or it's barreling out of that conduit, or whatever the gate might be. And then downstream we have tranquil flow, relatively flat slope, subcritical flow, and to get from the supercritical to the subcritical, it's going to do it quite abruptly in a hydraulic jump. Another situation was spillways. Spillways allow water to flow over a dam without damaging the dam itself. And you get water barreling down a very steep concrete spillway. When it gets to the bottom, it hits a flat slope, and there's lots of energy dissipation. And we want that to happen because we want to have all the energy dissipation in some sort of an energy dissipation structure like a stilling basin, a concrete stilling basin, before we let the water go to the natural river. Otherwise it would erode away down to bedrock. A drop structure and channels, drainage, flood control channels where the topography is such that if you just put the channel on grade of the topography, the velocities would be such that there would be tremendous erosion, and so you can have a drop structure where you drop a lot of the elevation difference in a concrete structure, and again let the energy dissipate here. And so again, just examples of hydraulic jumps, and the critical flow concept is very pertinent in analyzing those types of situations. We'll come back to that and look at it some more as we go, but just do an example problem now illustrating the basics. We've got a rectangular channel. It's concrete. That means the Manning's end's about 0.013. We've got a bottom width given as 12 meters, and it's abruptly changing from a slope of 0.01 to a slope of 0.005. So it's changing from a steep slope to a less steep slope, and we've got a discharge 25 cubic meters per second flowing in the channel, and we want to determine whether a hydraulic jump occurs. Now this illustrates the basic principles of using Manning's equation and using this equation that is valid for the condition of critical flow. And what we got to have, the only way we can have a hydraulic jump is for this to be supercritical flow and this to be subcritical flow. If that's not the case, we're going to get gradually varied flow, a very smooth transition between the two. If that is the case, where we've got water barreling down at supercritical flow and then transitioning to subcritical flow, it's going to do that quite abruptly with a lot of turbulence, a lot of energy dissipation. And if this is an earth-filled earthline channel a lot of erosion. And so we want to test that, and there's different ways of doing that. One thing we could do is use Manning's equation to estimate the normal depth here, and then use this equation to estimate the critical depth there, and compare the normal and critical depth to see whether we've got subcritical or supercritical. And then come down here, use Manning's equation to estimate the normal depth. And we're assuming uniform flow. We're assuming that there's no other irregularities, non-uniformities to cause any type of a non-uniform flow other than this break in channel slope right here. And so if you get some distance away from here where this isn't impacting the flow depth anymore, Manning's equation would describe the flow here some distance upstream and would describe the flow here some distance upstream. And so what I've done is just to eliminate one of the computations, what I'll do is compute the critical depth first. And so plug into this equation, plug in the discharge squared divided by acceleration of gravity. The area is easy for rectangular channels, so you hope for a rectangular channel on the exam because it's just the width times the depth. And the top width is given as 12 meters. And so we can solve directly and get the critical depth of 0.762 meters. Now again, this isn't necessarily with the depth, but this is the depth that you would have at the critical flow condition. We don't know at this point whether or not we have the critical flow condition. And so the actual depth, we're assuming uniform flow, that there are no other irregularities. It's an otherwise prismatic channel, and so we'll use Manning's equation. And and so what we've done, and again we could compute the depth upstream and downstream. What I've chosen to do just because I'm lazy and I could eliminate one computation and just compute, instead of computing a depth upstream and a depth downstream, that's two numbers, I'm just computing one slope. And so using Manning's equation, you need the depth, so we're going to say the critical depth is 0.72 meters, and so I'm asking myself the question, what slope would make the uniform flow occur at that depth? And so I compute the area at that depth. Now compute the wetted perimeter at that depth, the hydraulic radius, which is the area divided by the wetted perimeter at that depth, and then the velocity at that depth is the area divided by the area, the volumetric flow rate divided by the area's velocity. And so having computed these terms, I can plug into Manning's equation. And so here's Manning's equation from last week, and we know everything now except the slope. And so I'll solve for the slope. Solve for the slope, plug in the roughness coefficient, plug in the velocity I've just computed, plug in the hydraulic radius I've just computed, and I get a slope of 0.00212. Now, that's the slope that I would have to have for a uniform flow depth of 0.762 meters to occur. And the significance of the 0.762 meters, that's critical flow depth. And so then I've got to think, what is it do I actually have? My real actual slopes are 0.01 upstream, 0.005 downstream. And so I need to have supercritical flow upstream, subcritical flow downstream in order for the hydraulic jump to occur. And so to have supercritical flow, the slope has to be steeper than 0.00212, and 0.01 is steeper, so I do have supercritical flow upstream. So when I come downstream, for the jump to occur, I've got to have subcritical flow, and that's a very flat, tranquil flow, and low velocity means flat slope, and I've got a slope of 0.005, which is greater than this slope of 0.00212 at which critical flow occurs, so I've got supercritical flow. So I've got supercritical flow in both cases. And so if you got supercritical flow going into supercritical flow, there's no jump. You've got a smooth transition. Okay, well, we're going into a new topic, but it's going to all be related, and we'll be talking about hydraulic jumps in just a few minutes again. But we need to talk about water surface profiles. And this is non-uniform flow. We've talked about the Manning's equation being the basic flow equation for uniform flow, and in uniform flow, prismatic channel, the gravity forces making the water flow downstream are in balance with the frictional resistance of the channel bank holding it back, and so the depths and velocity and all the flow characteristics are constant along the length of the channel. Now, if something happens, some non-uniformity, you get non-uniform flow. For example, and this is just a common scheme that's been in textbooks and references for many years to classify different types of non-uniform flow. Now, let my pencil represent a dam. Say you put a dam here, you're going to have a backwater effect. And so what happens, well, let's look at the flow scheme for just a moment. M for mild, S for steep. Mild means subcritical flow, steep means supercritical flow. Mild slope, low velocity, subcritical flow. Steep slope, high velocity, supercritical flow. And then we've got three depths we're looking at. The normal depth, and the normal depth, that's the uniform flow depth. That's the depth you would have if there was nothing causing non-uniformities. The critical depth, of course, we've talked about. And so for an M1 profile, well, the actual depth is the real actual depth. And in this case, the actual depth is greater than both normal and critical. That's called a 1. And in another case, the actual depth is between normal and critical. That's the 2. Another case, the actual depth is less than both normal and critical. That's the 3. And so 1, 2, and 3 relates the three different depths. Mild and steep relates super versus subcritical flow. Now, in this case, this is called a backwater curve. This means you've got a bridge that's constricting the flow, or you've got something that's constricting the flow, a dam, or something that's causing it to back up. Now, if you've got a mild slope, you've got gradually varied flow. If this happens to be a dam, I'll put this pin here to represent the dam or whatever's backing the water up. It's going to be a smooth transition on back. If you happen to have a steep slope, supercritical flow upstream, you've got water barreling down, so when you back it up, you're going from a flow depth that's less than critical to a flow depth that's greater than critical, and you're going to have a hydraulic jump up here someplace. Now this would be a drawdown curve, and this could be represented, let me break the slope. If my pencil represents the slope, if you break the slope, make it steeper, the water's going to draw down. M2 profile. If you up here say you had a slope that was flatter on this one, and then this gets steeper, you'd have an S2 profile. And so the point we're trying to make, there's a lot of different ways that you can change the slope. You can have contractions, expansions, blockages to flow to make for different types of non-uniform flow. And now we're moving into the field of water surface profile computations. And this is an civil engineering computation that's done perhaps more than almost any computation I can think of. And a lot of the things that we'll be talking about tonight, the subject matter, is very common in civil engineering process, and the actual work is usually done with computer software packages. And probably, I've seen no survey to back up what I'm about to say, but I would guess that probably two of the most widely used of the water resources related computer programs in the U.S. today are a set of programs developed by the Hydrologic Engineering Center of the Corps of Engineers. One's called HEC1 Flood Hydrograph Package, and the computations in that computer program we'll be covering later in conjunction with hydrology. The second one is called HEC2, Hydrologic Engineering Center 2, Water Surface Profile Computations. And that's what we're covering at this moment. And HEC2 is a program that does standard step method, a solution of the energy equation, water surface profile computations. And these HEC1, the hydrology, gets you the discharge rates associated with given probabilities, and then the water surface profile computations delineate how high the water's going to get and what land's being covered. And the reason these programs are used so much, they were developed by the Corps of Engineers in the Water Resources Development Program originally for use in designing all types of flood control projects, levee projects, channel projects, reservoirs, spillways, and so forth. And then with the National Flood Insurance Program came along, and FEMA requires the delineation of floodplains in communities throughout the country. And the Federal Emergency Management Agency administers the program at the federal level, but every city in the country has their 100-year floodplains delineated in every creek and every stream. And so if you go buy a house, they're going to check whether or not your house lies in the floodplain, and if it does, you've got to get flood insurance. And if you want to build a house, the city of Killeen or the city of Temple or the city of College Station here, to get a permit, they're going to make sure you meet certain regulations related to not building in the 100-year floodplain. Now, for the cities and to regulate the use of floodplain land, and for the FEMA to administer its programs, you've got to be able to delineate the floodplains.
Hey,
We don't see anybody.
we hear your voice. Us neither.
The other
Now we do.
modem, it isn't hooked up yet, the other line.
We're good.
There it is.
There we go.
There we go.
All right.
Okay, back again. Are we okay,
Yeah,
Gary?
we're ready to go.
Ready to go? Okay, we were just making the point that water surface profile computations are quite common. And what we want to do now is look at the basic hydraulics of how to do them. And the basic concept is the energy equation. And we used the energy equation last week in pressure conduit flow. We'll use the same old energy equation in open channel hydraulics as well. Looks a little different though. We write it this way: the elevation head's the same. The pressure head, instead of writing P over gamma, we'll just write Y1, the flow depth. And so the elevation head plus the flow depth plus the velocity head. At an upstream section is equal to the elevation head plus flow depth plus velocity head downstream plus the head loss in between. And so we'll use that. And the real problem that we have and never really have been able to work out in the last 100 years is the head loss term. And so what we do with the head loss term, we use Manning's equation. Now granted, Manning's equation is a uniform flow equation, and we're solving non-uniform flow problems when we're doing gradually varied. And gradually varied means there's no hydraulic jump or hydraulic drop problems. But for this one term, the head loss, we'll use Manning's equation to estimate the head loss. The terms are defined, and this is a key diagram, of course, is relating the different terms in the energy equation. And elevation head, depth, velocity head upstream, elevation head, depth, velocity head downstream, the difference being the head loss. Now we have uniform flow, which we don't anymore, but back last time when we did have uniform flow, the channel bottom, water surface, energy line were parallel. Now gradually varied flow means the depth changes along the length of the channel. And so what we'll be doing is having a known depth someplace, computing the depth all along the channel. There's two ways of doing that. Conceptually, we're working with energy equation using Manning's equation to estimate head losses either way, but the computational details vary between the direct step method and the standard step method. The direct step method, if you get a question on the exam, I would guess it would probably be the direct step method because it's easier to use, and the direct step method works only with a prismatic channel, and as we go we'll see why it's only valid for a prismatic channel. Prismatic channel means you got a constant everything. You got a constant, the slope stays the same, the bottom width stays the same, the geometry, everything's constant. And so you're basically talking about a man-made channel. Now, if you've got natural channels, everything changes. The geometry changes continuously in a very irregular way, and you've got to use the standard step method. So the standard step method you can use for any channel. The direct step method you can use only for prismatic channels. But the direct step method does not require an iterative solution. The standard step method does require a trial and error iterative solution, which slows you down if you're trying to do it with a calculator on an exam. Direct step method first. And so we're deriving the basic concept here. Everything's based upon the energy equation, so we write it first. So there's our old friend, the energy equation, the workhorse of hydraulics. Remember, the slope of the energy line, if you remember back to the diagram, is just the head loss divided by the distance between the two sections. And then just solve for the head loss. So the head loss is just the slope of the energy line, and a common term for that is the friction slope. And because it's called the friction slope so often, we'll just use a subscript F. And then the delta X, that horizontal distance between cross sections. Now the slope of the channel bottom is just the difference in the elevation of the channel bottom, the difference in the elevation head divided by the horizontal distance between the two sections. And so we can express the difference in the channel bottom elevation at two sections as the slope of the channel bottom times the distance between the sections. And now we're taking the energy equation, rearranging it, and this is a simple algebraic rearranging of terms in the energy equation. And so basically this says specific energy. Remember, specific energy is the depth plus the velocity head. Specific energy upstream minus specific energy downstream is equal to the difference in elevation of the channel bottom between the two sections plus the head loss in between. Simple rearranging of terms in the energy equation. We've got an expression for head loss. We developed it right here. So plug in this expression for the head loss. We've got an expression for the difference in the channel bottom elevations. The elevation heads, we call that. And so we plug in there, and then we solve for this delta X, and you do a bit of algebraic rearranging, and you get this basic equation. That is the basic equation of the direct step method for gradually varied water surface profile computations. And so if I wanted to write it in shorthand notation, recognizing within the parentheses the depth plus the velocity head, that's also called specific energy, energy with reference to the channel bottom. And so I could say E1 minus E2. Friction slope, that's the slope of the energy line, S sub F. The S sub naught, 0, that's the slope of the channel bottom. And so that's the difference in slope between the energy line and the channel bottom, and specific energy upstream, specific energy downstream. So all we're doing now is at two sections, knowing all of this information, we can compute the distance between the two sections. We do need a way to estimate the friction slope. And of course the friction slope is just the head loss divided by delta X, so we got to be able to have a way to estimate the head loss term. That's an expression of head loss, and we use Manning's equation. And again, as I pointed out before, I'm recognizing that this is an approximation. We've got a clearly non-uniform flow problem in which we're using a uniform flow equation for. And so what that's going, well, we'll talk about the implications of that in a bit. Manning's equation I've reproduced here from last time. And Manning's equation has its velocity is 1.486 times the roughness coefficient times the hydraulic radius to the 2/3 s to the 1/2. It's the S. Now that's the slope of everything. That's the slope of the energy line, the channel bottom, and the water surface in uniform flow. It's the slope of the energy line now. And so we'll solve for S, and that's the slope of the energy line. And the thing is, what velocity do we use? The velocity is different upstream and downstream. What hydraulic radius do we use? It's different upstream and downstream. Well, we'll approximate the velocity as the average velocity, just average of the upstream and downstream, and average the hydraulic radius upstream and downstream, and use the subscript average for that. If we wanted to do this in metric units, same thing, just the constants different in the metric units. So that's it, and we'll go through it now in the context of an example problem, so we'll have some numbers to look at. And so in the example, we've got a 15-foot wide rectangular channel. The Manning's roughness coefficient is 0.0015, and the bottom slope, that's the longitudinal bottom slope, 0.0015. And I found a typo. So that must mean that the channel bottom slope should be 0.015. I've got an extra 0 in there. Can you fix that in your notes? We've got to change the Manning's roughness coefficient to 0.015. Okay. The channel discharges into a river which may reach a stage of 10 feet above the channel bottom during floods. And we've got a design discharge of 500 cubic feet per second. And so we want to calculate the normal depth, the critical depth, and the distance from the channel outlet to the location where normal depth occurs. And so we basically have a flood control or drainage channel here that's been built by people. And so it's rectangular concrete channel, and it's discharging into a river. And so we know the stage of the river, and we want to now compute the depth of the water in the channel all the way upstream. Now, if you get far enough away from the river, you can use Manning's equation. It's a prismatic concrete channel, a constant bottom slope of 0.0015, a constant bottom width, a constant rectangular channel section. So we can use Manning's equation to compute the depth. However, what happens is the backwater effects from the river into which the channel is discharging causes a non-uniform flow situation. So one question right offhand, are we going to have a hydraulic jump? Are we going to just be a uniform flow until we get almost to the river and have a hydraulic jump? Or will there be a smooth transition over a long distance, half a mile, 2 miles, very smooth transition from the normal depth to the uniform depth? And we can, or to the 10-foot depth in the river. And so to answer these questions, we need to know what the normal depth is and what the critical depth is. And so we'll just compute them. And Manning's equation we used last time. It continues to be used over and over again. Another workhorse of hydraulics. And so we want to compute the normal depth, the depth at which uniform flow occurs. And so we use Manning's equation. The area and the hydraulic radius are both a function of the depth. We know everything else. So we take the area, the hydraulic radius, and put it on the left-hand side of the equal sign, with everything else on the right-hand side of the equal sign. This some people call AR to the 2/3 the section factor. And of course that is a function of the depth which we're solving for. Now the flow rate is given as 500 cubic feet per second. The Manning's roughness coefficient is 0.017, Well, if it's 0.017, and I'm sure that's a good number, and so what we'll do up here is change it to 0.017. So in the problem statement, we'll say the Manning's roughness N is 0.017, and correct that. And the slope is the 0.0015, and then the constant there. Now we need an expression for the area. If you've got a rectangular channel, the area with a width of 15 feet, the area is just 15 times the depth. We need an expression for the hydraulic radius. That's the area divided by the wetted perimeter. The area is 15 wide. The wetted perimeter is the bottom width is wetted, 15 feet. And then on either side, you've got the depth, which is a wetted surface. And so 15 plus 2y would be the wetted perimeter. And so the only unknown in that expression is the depth y. And so you solve for the depth, and I did it by trial and error, and got 4.8 feet. So that's the normal depth. That's the depth that the water would be flowing at if it hadn't been for the backwater effects of that 10-foot deep river. And so we need to know what type of a flow condition we've got, and knowing the critical depth allow us to figure that out. And so here's our critical depth equation we've used in the previous example. I've reproduced the equation which we derived a few minutes ago. I plug in the numbers, the 500 cubic feet per second, square it, the 32.2 feet per second squared is the acceleration of gravity. The top width, bottom width, any width for the rectangular channel is 15 feet. The area is 15 times the depth, and we solve for the depth, and the depth is 3.26 feet. So what does that tell us as far as the flow conditions to anticipate? We've got a normal depth of 4.8 feet. So if you get far enough away from the river, up the creek, up the channel, up the concrete channel, if you get far enough away from the river so there's no effects, the depth's going to be 4.8 feet. But it's flowing into the river, so the depth's going to be 10 feet in the river. And so you're going from 4.8 feet to 10 feet. Now, critical depth is 3.26 feet. So we're not going through critical depth at all. So we're going from subcritical flow to subcritical flow. There will be no hydraulic jump. There's no supercritical flow involved in this problem, so we've got a gradually varied flow situation, and we can simply use the energy equation. So how far away from the river do you have to get for the depth to actually be 4.8 feet? And we'll compute that along with our water surface profile on the next page. So on the bottom here, we've drawn the schematic. Here's coming out of the paper, horizontally out of the paper is the river, 10 feet deep. Then we've got the concrete channel emptying into the river. Someplace up here, the frictional forces and the gravity forces are in balance, and we've got a uniform flow depth of 4.8 feet. But this 10 feet is throwing it out of balance. We've got a backwater effect, a non-uniform flow. And we know there's no hydraulic jump, so I can draw that in as a smooth, gradually varied flow. And so what we'll do is compute the depth at different locations along the channel now. And so we'll apply the energy equation, and actually what we'll do is we'll assume different depths. If we're going to go from 4.8 feet to 10 feet, and we'll actually work our way backwards from 10 feet going back upstream, you got to go through 9 feet someplace, you got to go through 8 feet someplace, 7 feet, 6 feet, 5 feet, and so forth. And so you're going to get from 10 feet to 4.8 feet. Someplace you're going to be at a depth of 9 feet, someplace at a depth of 8 feet, and so forth. And so what we'll actually compute is the location, the delta x. And so if we go back to our basic equation, and we'll just be plugging into that equation over and over again. I'm going to flip back to it a few notes back. The direct step method For gradually varied water surface profiles, we're computing the delta X. And so what we'll say is at some place the depth is 10 feet. We'll plug in 10 feet here. We'll plug in 9 feet there. We'll compute the horizontal distance between the 10-foot and the 9-foot depth. Then we'll do it all over again. We'll plug in 9 feet for Y2, 8 feet for Y1. Then we'll do it all over again. And just keep plugging into this equation over and over again. And of course we'll have the friction slope term, and we'll be using the Manning's equation to solve for that. And since I'm just repeating myself, I'll set up the computations in a table. And here's the table. I've listed the different depths, and we can just look at, we're just doing it, that's why it's called direct step, because we're just stepping through distance here. Someplace the flow depth is 10 feet, someplace upstream the flow depth is 9 feet. And you can easily compute the different values that you need to plug into the energy equation. We need the hydraulic depth, the velocity. The hydraulic depth is just the area divided by the wetted perimeter. And so we know that the area is the discharge rate divided by the the area is just 15 times y. The width is 15 feet, so 15 times y is the area. Then the wetted perimeter is just the bottom width times 2 times the depth. We can divide one by the other, get the hydraulic radius each time, divide the 500 cubic feet per second discharge rate by the area to get the velocity. And then specific energy is just the depth plus the velocity hit. And so velocity squared divided by 2g plus the depth. And we've got the specific energy upstream and downstream. We need to get the friction slope, the S term. We need an average velocity to plug into Manning's equation. We just average those two velocities. We need an average hydraulic radius to plug into Manning's equation. We just average these two hydraulic radiuses together. We plug them into Manning's equation. You can go back in your notes. We're just a page or so back. We've got Manning's equation written in terms of an S. We solve for S. And so we know the S, we know the specific energy upstream and downstream. We plug into our energy equation to get the X, the difference between those two sections. And then I keep a column to accumulate the X. Having done it, we can do it all over again. So we go down another line and look at one section the depth is 9 feet, at another section the depth is 8 feet, and we do the same computations all over again. And we just keep going. And so what I've done is there's 10 feet, someplace the depth is 9 feet, and I use the energy equation, and I computed a value of 762. And then someplace the depth is 8 feet. I used the energy equation, did the same computations, and got a 799 feet here. And then someplace here the depth is 7 feet. Used the energy equation, got a horizontal distance here of 871. Okay. And so we've got the water surface profile. We've got the depths at different locations, and then we get uniform flow, and then once we get to uniform flow, it stays at 4.8 feet all the way upstream until something changes. The slope breaks, the width changes, some backwater effect, or something of that nature. One of the things that I did somewhat arbitrarily here is I used a delta Y, a step size of 1 foot. And that was somewhat arbitrary, and recognize we used Manning's equation to get the S. And we just plugged in an average velocity and an average hydraulic radius into Manning's equation to get the slope term, slope of the energy line. And so the smaller the step size, the less approximate is that simplification. So if I make the step size smaller, I get a more accurate answer. And just for fun, I'd ran this out on a spreadsheet, and I just ran it out with different step sizes. And by the way, the total distance down here at the bottom, all the way from 10 feet to where uniform flow occurs here, is this number, the 6,901 feet. And that's using the 1 foot step size. And just did the computations over. You got a couple other solutions in your notes there. Here I was very coarse. I went from 10 feet to 6 feet, 4 foot step size, and then from 6 to 5, and I got a 6,899 instead of a 6,901. So that's still pretty close. And then I got more accurate, and I used a 1/2 foot step size. And when you run it, all the computations out all the way from a 10 foot depth to a 4.8 foot depth at a 1/2 foot step size, the horizontal distance came out to 7,025 feet, which is pretty close to that 6,901 I got before. So basically, I'm not too sensitive to step size, as long as it's relatively small. Everybody with me on that set of computations?
Yep, pretty easy.
Okay.
Straightforward. It is straightforward.
Okay.
A lot of calculations to it.
Does it jump out at you why you can't do that for a natural river? If you're doing the floodplain delineations for Fort Hood and Colleen and in that area, and someone's already done it, and they get updated periodically, and the first thing you're going to do is one of two things. You're going to send a surveying crew out to take cross-sectional data at different locations in the stream, or you're going to take cross-sectional data off of a topographic map, if you already have a topographic map for the creeks and the streams and rivers. And so having done that, what you've just done is set the location of every cross-section. And you have to do that because the stream varies. You need cross-sectional information, elevation versus horizontal distance data, to characterize the cross-sectional geometry of the stream at different locations. But you've set the basic locations of the cross-sections at the very beginning to get the basic data. So there's no way you can solve for delta x's. The delta x's you've set at the beginning. And so what you got to solve for is the depths. And so this is the same thing almost, but the computations are a little different. And this is the HEC2 approach, or all the different water surface profile computer programs do this. And so we call this the standard step method for computing water surface profiles for gradually varied flow. Energy equation hasn't changed a bit. Same old energy equation we've been working with before. Now the head loss is still the friction slope times the length of the reach of channel, and we're still estimating the friction slope using Manning's equation. No difference there. Here's what's different. Instead of taking an assumed y1 and y2 and computing a delta x, we're taking a set delta x and computing y2, given that we know y1, or vice versa. And so I've said it this way: with a depth y2 known, we iteratively solve for y1 by adjusting y1 until both of the following expressions result in the same value for h1. h1 is the total head. The total head at the upstream location is the elevation head plus the depth plus the velocity head. That's a good equation. It's got to hold true for whatever y we assume. And also, the head at the upstream section is equal to the head at the downstream section plus the head loss in between. So both of those expressions are true. And so we've got to set up an algorithm to do that. And the number crunching gets a little time consuming here. So hopefully, and it would seem to reason what they would do on the exam is to give you prismatic channels, something that's easy to work with, like a rectangular cross section where you can use the direct step method. But what I've done here is taken that rectangular cross-section and just illustrated the standard step method, and I'll run through it very quickly. And so what we're doing, using the same geometry as before, though this method does not limit itself to that simple prismatic channel. It could be a highly irregular natural river that we're working with, just as would be just as pertinent. And so what we do here, we set the stations. That's the difference. The different cross-sectional locations are set at the beginning, and we've got to know a starting condition. And we know that from the problem statement. The river into which the channel is flowing is at a depth of 10 feet. So given the 10-foot starting elevation, we can run through the computations. And I don't think I'll take a whole lot of time on this simply because we've got so many things we need to cover tonight. But basically what we're doing is, in the first line of the computations, we're given the depth of 10 feet, and given that once you know the depth, you can compute everything. You can compute the area, the velocity head, and then the velocity head plus the depth plus elevation head, and the total head. And then you can compute the hydraulic radius, and you can compute the slope from Manning's equation. So once you got the depth, you can compute everything from simple equations. Now the problem is we don't know the depth. And so what we're doing here, the first line is just to give us basic data, and so we're working upstream now. So at the end of the channel where it empties into the river, the depth is 10 feet. I don't know the depth. And so what I'll do, I've got to assume a number right here in your table. That's the number I don't know. And I know it's something less than 10 feet. As you go up the concrete channel, the depth decreases. And so I make a guess. And after I make a guess of the depth, then I can compute everything. I can compute the area, the velocity head, the total head, the hydraulic radius, the slope from Manning's equation, and then knowing the slope from Manning's equation at that section, and at that section I can average those two together to get an average slope, and then I use that average slope and the distance between the two sections to get a head loss term. And then I know that if I take the total head at the previous location plus the head loss, I've got to get the head at this location. And then I know that if I take the head at this location and subtract from it, that's the total head, elevation head plus pressure head plus velocity head. If I subtract from it the velocity head in this column minus the elevation head in this column, the only thing left is the depth. So that depth comes out to be this initially assumed depth. I'm home free. But in general it doesn't. So the first time through, this might come out to be 9.5. So then you got to take the 9.5, plug it back in, and do the computations over again. You got to keep doing them over and over again until you're assuming a depth, and then all the computations are coming out so that if you back the depth out, you get the same depth. Another way of saying the same thing, everything's got to hold simultaneously. This expression's got to be valid. The head's got to be equal to the elevation head plus depth plus velocity head, and then the head upstream's got to equal the head downstream plus the head loss. And so I've just set up the algorithm that using both of those terms, and you just have to iteratively do it. And I think I'm going to move on unless you've got comments or questions, and take a look at conservation of momentum. And I'll speed up just a bit. We do have quite a few topics here, but conservation of momentum is quite useful in dealing with hydraulic jumps, because what happens in hydraulic jumps is you've got such turbulence, there's such a high amount of energy loss that it's quite obviously you can't use Manning's equation to estimate energy loss. You don't have anything to estimate energy loss. And so we're not going to try to estimate energy loss. We're going to instead of conserving energy and looking at energy terms, we're going to work in terms of a conservation of momentum. And so basically what this page does, it defines the basic terms. And so you can read through there and look at the diagram and define basic terms. And then the second page uses those terms and Newton's second law of motion to derive a basic equation. And I'm going to skip through and look at the equation. There it is. And that's our specific momentum equation. What it says is the specific momentum upstream is equal to the specific momentum downstream. And so we've got q squared over acceleration of gravity times the area upstream plus the distance from the water surface to the centroid of the area upstream times the area, the cross-sectional area flow upstream equal to the same terms downstream. We're moving right down the road here. We're in supercritical flow here in the way we're going to move through these notes here for a bit. But here's the equation. That's the specific momentum equation. And I want to approach it from a very typical application, and that's analyzing what's happening in a hydraulic jump. Now, basic textbooks will continue the derivation, and whereas this equation is good for any type of geometry, if you have a simple case where you've got a rectangular channel with a small slope, you can take the basic equation, which is conservation of specific momentum, and go through some derivations and come up with these equations. So this is a general equation that's good for any geometry. These equations express the same concept, but they're only good for a rectangular channel. And it's got to be a small slope. Now, before we looked at a diagram like this in which we were looking at specific energy, and momentum's sort of the same shape. The shape's a little bit different, but it's the same general analogous concept. The critical flow, by definition, is the condition in which the specific momentum is a minimum. Before we said the specific energy is a minimum. Both conditions hold true. And so for a given specific momentum, I'm plotting depth versus specific momentum here. For a given specific momentum, there's two different depths that have that same momentum. We call those sequent depths. And if we use the application of a hydraulic jump, what that would represent is the depth before the jump and the depth after the jump. So we've got the same specific momentum before and after the jump, and so the equation holds true in both places. We call those sequent depths. Those are the two depths at which the same specific momentum holds true. And so what that does for us, it allows us to analyze a hydraulic jump. Given the depth before the jump, we can compute the depth after the jump or vice versa. And so in this problem, we've got a hydraulic jump occurring a triangular flume having side slopes of 1:1. The flow rate is given at 0.45 cubic meters per second. The depth before the jump is 0.3 meters. Compute the depth after the jump. And so it's a problem in just plugging the numbers into the equation. There's a specific momentum equation, which I let you at your convenience go through the derivation on the previous page of notes. That's the basic equation, and here we're plugging in the numbers. We know the depth before the jump. We want to compute the depth after the jump. And just knowing the geometry of a rectangle, we can plug in the numbers. The flow rate's 0.45 cubic meters per second. It's the same upstream and downstream. We can plug that in. The acceleration of gravity is a constant. We can plug that in. The area of a triangle is, for this triangle, is y squared. The z bar, the distance from the water surface to the centroid of the area, is 1/3 y. And so from that geometry, we can plug in for z bar and the area, and we know everything except the depth. And then we can solve for the depth. And so given the depth before the jump being 0.3 meters, the depth after the jump is 0.858 meters. This is another classic problem of fluid mechanics. And we're using both the energy equation and the momentum equation in this problem. And what we want to do is estimate the flow depth in the downstream channel and the energy loss in the hydraulic jump at the foot of the 100-foot wide rectangular broad-crusted spillway for a discharge of 2,130 cubic feet per second. So we're given the depth upstream. So the first thing we want to do is, knowing the depth upstream of the dam, compute the depth at the toe of the spillway, and we'll use the energy equation to do that. And then, knowing the depth at the toe of the spillway, we'll compute the depth downstream using the conservation of momentum equation, because we're forced to do that because the hydraulic jump is dissipating so much energy that we cannot compute that head loss any other way. And so, let's see, we're plugging into the energy equation between 2 points. So pick a point there. There's point 1. I actually called it point 0, and picked a point here and called that point 1, and apply the energy equation between those 2 points. And so, let's see, velocity is discharge divided by the area. And so, if we take the discharge there, divide it by the area there, we're going to have the velocity. So I've got an expression for the velocity, and so plugging in, we'll let I will just take this line, and that'll be our reference datum. And with that as a reference datum, the Z0 is 0, the depth is 44 feet. At that location, the velocity head, we're going to assume 0 velocity. We'll get upstream of the dam, back in the reservoir, where the reservoir is very wide, so the velocity is very small. Assume 0 velocity. Then at point 1 here, again, Z1 is 0. The depth is what we're solving for, Y1. We've got an expression for the velocity we plug in, divided by 2g, and we're going to make an assumption here. We're assuming 0 head loss. We're assuming in this channel that there's pretty smooth flow, very little turbulence, and we'll use 0 head loss and get the depth here of 0.4 feet. Knowing the depth here is 0.4 feet, we want to get the depth here using conservation of momentum. In other words, we want to compute the sequent depth. And so I'll use this basic equation. And so we want to compute the sequent depth, and we need here's the basic equation reproduced from the previous page of the notes. That's for a rectangular channel. And so we take our depth that we just computed, plug it into the expression from the previous page to get the velocity, use the velocity to compute the Freud number, and then plug in for the Freud number. And what this is doing for us is giving us the relationship between the depth upstream and downstream of the hydraulic jump. And so given the depth given the depth upstream of the hydraulic jump of 0.4 feet, the depth downstream of the jump is 8.2 feet. Now, if we wanted to, an alternative way of doing that, this equation is valid only for rectangular channels. This equation is valid for any type of geometry, including a rectangular channel. So here we've just used the basic conservation of momentum equation, Pacific momentum equation, plugged in the numbers to get the same answer again. So the equations do give identically the same answer. To compute the head loss in the jump, we can
Ralph?
Yes.
What does Z bar represent? Is that the centroid of that shape?
It is. It's a distance from the water surface to the center of gravity of the flow area.
Okay, so the center of gravity. Okay.
Uh-huh.
That's what I figured. All right, thanks.
Uh-huh.
I'm looking at that one. I figured that's what it was. 1/3.
Okay, to get the energy loss in the jump, instead of using an equation to estimate energy loss like Manning's equation, we'll just simply compute the energy upstream and compute the energy downstream. And we know everything we need to know to do that. the total energy, specific energy, will be the depth plus the velocity head. The elevation head's the same upstream and downstream, so we'll just leave it out. And so before the jump, the depth is 0.4 feet. The velocity is 52.25 feet per second, a tremendously high velocity. The water's really barreling off of that chute, divided by 2G. So we get energy upstream of 44.4 feet. After the jump, we computed a depth of 8.2 feet. We've taken the velocity, squared it, divided by 2G to get the velocity head, and so the total energy downstream of the jump is 8.4 feet. So we've gone from a total head of 44.4 feet to 8.3 feet. And so, well, if we wanted to express that as an energy loss in percent, we lost 81% of the head. If we take just a moment here and go back to this page of the notes, and let's say we do a couple of things. We can use any of the hydraulic jumps we want. Let's go ahead and we just did some work with the spillway. Let's say that we do the computations we just did. We computed that depth, and having computed that depth, then we use conservation of momentum to compute this depth. And it came out like so. Then let's say we went back to the water surface profile computations, and we started downstream here someplace, did backwater computations using the energy equation, the standard step method solution of the energy equation, and we worked our way up and we computed a depth. Oh, let's say we computed a depth right here. And engineers would call that the tailwater depth. Uh-oh, so what's wrong? I did two sets of computations. Let's go through the computations again. The last example, I used conservation of momentum. Given the depth before the jump, I computed the depth after the jump. I did it correctly. You know, I'm not going to make a mistake here. So that is correct. Now, I did another very conventional type of a computation. I started, say, back in a river that the discharge channel is discharging into. With an elevation there, I computed the tailwater depth. I worked my way back upstream, standard step method solution of the energy equation, and I got a depth right here, which is different than that depth. So what's the right depth? What's happening here? No errors. I did the computations correct. And actually, both of the depths are correct. But obviously, we can't have two depths. The water's not going to jump up to there, then drop down to here. So what is happening there? And that's a very common design problem. What's happening is we're not going to have a jump right here. We're not going to have a jump until those two sets of computations come out the same. And to make them come out the same, what's going to happen, this water, when it comes barreling down this chute, it's going to keep barreling. And it's going to keep barreling down, and there's going to be some frictional resistance that slows it down just a bit, and the depth is going to increase, and it gets far enough out downstream, and finally the two match, and when the two depths match, then you have a jump. So if you build a concrete channel, a concrete apron right there, and you're expecting the jump to occur right there, but the tailwater's too low, and the jump comes off of the apron and occurs down here someplace, it's going to erode away the earth, and this whole thing's going to break off. And so that's a common problem in spillway design. What you would do is try to lower the apron so it's low enough so that the tailwater matches up with the sequent depth so that you have the jump right here. If you had another condition, say the sequent depth is right here, same place, but the tailwater's up here. Now, the tailwater is set not by what's happening upstream. This is subcritical flow. When you got subcritical flow, that tailwater is the backwater from what's happening downstream. And whatever is happening downstream is causing the water to be up here someplace. Now, you got water barreling off of here, this supercritical flow. You're going to have this hydraulic jump, but what's going to happen, it's going to jump up here someplace so that the sequent depth matches up with that, and you'll get a jump up here. And we'll call that a drown jump. That's typically not quite so bad. At least you're jumping on the concrete. You're not having your jump run off the concrete and cause severe erosion problems downstream, but you lose a lot of the efficiency in that you don't lose 81% of the energy. You lose less energy that way. Probably the best thing for us to do now is if you've got any questions, let's talk about them and answer questions, discuss anything you'd like to discuss, and then take a break. And then after the breaks, switch to a closely related but different topic of hydrology. Any comments or points of discussion before we take a 5-minute break? Well, how about if we take 5 maybe, and then come back and...
Hey, Rob.
Go ahead.
I was going to check on something, too. Is anybody getting ready to take that quiz and you need some books to haul in with you that we haven't already sent down?
I haven't heard anyone who still needs some.
All right.
I know I'm set.
All right, that's fine. I just want to check, that somebody didn't say, well, I don't have a surveying book, or I don't have a hydraulics book, or something like that we could dig up for you, and send it down. But if everybody's okay.
The only thing I saw that I might want is the highway capacity manual. But you guys talked about copying some tables out of one of those, and I think it was the highway capacity manual, because you don't need the whole manual. You only need a certain, a couple chapters.
Those have been copied and sent down because they just sent me my copy of them today, so they'll probably be down there in a day or two.
They must be on the way then, because I noticed. I asked Rhonda about that, and she didn't know.
Okay.
But as I was going through problems the other night, that was about the only thing. Some of the things in Lindbergh references the highway capacity manual. Of course, I don't have that, but
all right.
That's because I'm not a civil engineer.
When you get a set of notes that says appendix for transportation stuff, see if those are sufficient to do what you were trying. If not, get back with me.
Okay.
Okie doke. See y'all in 5 minutes.